Hello and welcome to our lesson on multiplying and dividing complex numbers in trig form. Now before we actually get to the multiplying and dividing of the complex numbers in that trig form, we're going to start with some review. We're going to multiply complex numbers in their rectangular form, the standard form, the form we're used to, because the process ultimately is the same when we apply it to our trig form. And then ultimately we're going to be able to do some streamlining, so hopefully you'll appreciate that after the work we're going to look at in just a few minutes. So we're going to start again with some review. Let's find the product of these two complex numbers that are in rectangular form. That's the standard form that we're used to seeing complex numbers in. So we're just going to multiply. So we'll start here with the product of 1 and 2 radical 3, which would just give us a 2 radical 3. We can multiply here. 1 times 2i is going to give you a positive 2i. Multiply here, so a negative I times 2, it makes our coefficient negative 2i, and then we have radical 3 times radical 3, which is just going to be 3, but if you wanted to make that radical 9 in the initial step, that's fine. And then the final product here, negative I times 2i makes a coefficient of negative 2i squared, and then we have that radical 3. And so let's now just simplify this. So I don't see any like terms right out of the gate. I'm just going to bring down then the first term, bring down the next term, fix these next couple. I don't have enough colors here. We know, again, radical 9 is just going to make 3. We also should recognize I squared gets replaced with negative 1. So my third term goes from negative 2i times radical 9 to negative 2i times 3. That's going to make it negative 6i. And then if we replace I squared with negative 1, the negative 1 times the negative 2 makes a positive 2 in front of our radical 3. And now I have two sets of like terms. So I can combine the 2 radical 3 that I have here with the 2 radical 3 that I have there. That's going to make 4 radical 3 altogether. And then I can also combine the 2i with the negative 6i, and 2 minus 6 makes a negative 4i. And that would be the resulting complex number. So we multiply the two complex numbers, we get a complex number. Multiply them in rectangular form, we get the rectangular form of that product. Okay, so not too bad, just multiplying. Now that is exactly the same process when we're multiplying two complex numbers in trig form. It just looks a little worse, and in fact, because we have to write a little bit extra, it's going to feel worse, but it's just distributing. Now, in this next problem, that's what we're going to do. We're going to use that same process to find the product of these two complex numbers that are in trig form. But we really have to be careful, because right now this looks like we are multiplying a single term by a single term, but we are not. Remember, the CIS is the abbreviation for cosine and then plus imaginary sign. So if we are given this compact form of our trig, our complex numbers in trig form, we want to write the expanded, not the abbreviated form, to understand truly what we're doing. So the first thing I'm going to do is, again, rewrite this. I'm going to change my 2 cis 60 degrees to 2 cosine of 60 degrees, plus I times the sine of 60 degrees. And then we're going to try to multiply that with, again, the expanded form over here is going to be 4 times the cosine of 150 plus I sine of 150. So again, hopefully we can see how this is the same process. Now I have these coefficients. I'm going to just multiply those and make the one coefficient. And then really the focus is going to be on multiplying the binomial I have here with the binomial that I have here. So again, I'm going to start by just multiplying these two numbers. So that's going to give me a coefficient of 8. So multiply the radius of the first with the radius of the second. So new coefficient of 8. And then, again, multiply the binomial I have here with the binomial that I have here. And actually, I'm going to move this 8 over because I think I'm going to need a little bit of space. So that 8 is going to be multiplied by, yes, the product of these two binomials. So first, when I multiply here, we got to be careful not to do any incorrect math. Multiplying cosine of 60 times cosine of 150 is precisely that. Cosine of 60, cosine of 150. I can't actually multiply the 60 and the 150, right? Those arguments are attached to the cosine. So cosine of 60 times cosine of 150 becomes cosine 60 cosine 150. And then we're going to multiply here. Cosine of 60 times I sine of 150. is going to be positive cosine 60, and actually I'm going to write the sign first because the I is in front. So I sine of 150 and then cosine of 60, just so I can avoid writing in parentheses. Remember, work smarter, not harder. And now I'm going to multiply here. So I'm going to have a positive I sine of 60 and then cosine of 150. And then finally, running out of colors, let's go gray, multiply here. So I times I is going to give me an I squared. And then I have sine of 60 and sine of 150. How are we doing on space? Good. Okay, so there it is. Multiplying those two binomials produces the four terms, just like up here, multiplying two binomials produces those four terms using our product rule 4 times. Now let's try to clean this up, okay? I know that the I squared that I have, let's see here, I know that's going to be replaced with a negative 1, and that would mean this term and this term are going to be the terms that don't have the imaginary, and I could see that this term here and this term here are going to have the imaginary. So I'm going to replace I squared with a negative 1, and then I'm just going to rearrange these because I'm going to want to keep those terms that have the imaginaries together and ultimately factor, and you'll see in a second. So let me leave my 8 out here, and again I'm going to leave this, oops, turned my eraser on. I'm going to leave this cosine 60 cosine 150 alone. I'm going to replace I squared here with a negative 1 and move that term next. So it becomes a negative sine 60 cosine, no, just kidding, sine 150. And then my next two terms, not like terms, but in my next two terms, so these two terms that I haven't written yet, I have an I in common to those two terms. So what I'm going to do is factor the I out. So now I'm going to have a positive I that factors out of those two terms, leaving me a sine 150 cosine 60 plus sine 60 and cosine 150. And now we can close that giant set of parentheses. Okay, so we're getting close. Now this looks awful. I don't know if anything is jumping out at you, but what I am seeing is something that looks very familiar. So this cosine, cosine, sine, sine, or sine, cosine, sine, cosine. Actually, let me flip this one around. This one right here, if I have sine, cosine, and then cosine, sine, it feels even more familiar. So I'm going to rearrange these two terms. Let me call that cosine 150 and sine of 60. Remember, the order we multiply doesn't matter, so it's totally okay to rearrange those. But again, this should feel familiar. So let me go to my scratch paper here. If you remember, the sine of a sum, the sine of a difference, cosine of a sum, cosine of a difference, identities, right? That's what we're seeing here. So in the first part of this part right here is what I'm referencing. I have cosine, cosine, sine, sine, and a minus in the middle, and the angle here and the angle here, those angles are the same, right? Just like they are in our identity. So the identity that has the, sorry, I forgot what I had. Cosine, cosine, sine, sine with the minus in the middle. Cosine, really? Fat fingers can't go appropriately to the next box. Cosine, cosine, sine, sine with the minus in the middle. That is the cosine of a sum. So I can condense that thing that I have written there, that product, that expansion, to the cosine of the sum of those two angles. So that part that I highlighted in green there is going to be condensed down to the cosine of the sum of the angles 60 and 150. Okay, plus over here I have I times, again, something I can condense. It's sine, cosine, cosine, sine. So if I look at my formulas, sine, cosine, cosine, sine, and I have a plus in the middle, that means that expression that I have there can be condensed into the sine of the sum of those angles. So here, again, I have my I, but this can be replaced with the sine of the sum of those two angles. So it becomes the sine of, again, the sum of 150 and 60. Well, of course, I know how to add 150 and 60, so I can take this another step and call this 8. What happened to my pen? 8 times the cosine of 60 and 150 makes 210 degrees, plus I times the sine of 210 degrees. And it should make sense that those two angles end up being the same, because when we multiply two complex numbers, we should end up with a complex number. Now we do this in rectangular form, we end up with the rectangular form. If we multiply two complex numbers in trig form, we should end up with a complex number in trig form. And that's exactly what we see here. Okay, now, because I started with a condensed version, a condensed form in my product, I'm going to condense this one as well. So I'm going to condense this down. I'm going to call it 8 cis 2. I can't write. 210 degrees. Okay? So that is what the product of two complex numbers in that trig form or polar form, that's how it unfolds. This is what it looks like. But that is a lot of work. And I'm hoping that the theorem we're going to look at in just a second is going to streamline the work for us, because there's absolutely some connections here. Regardless of what the angles are, we know that the angles in our original problem, right, if we start with a complex number here, these angles will have to be the same. If we start with a complex number here, these angles will have to be the same. So regardless of their actual values, the same properties will occur every time I multiply. And so I always end up being able to condense using the sine of the sum and the cosine of a sum. Now, again, just to try to streamline the process, let's look and compare the condensed form of our answer to the condensed form of our product to see, can we just bypass all of this work if the same patterns are going to occur? Yeah, we can bypass some of the work by just multiplying the radius length here with the radius length here. We actually call that the absolute value of our complex number in trig form. Remember that radius length is the actual length of the radius would be the same as the length of the triangle, or like the magnitude of a vector. It's the size of that thing. So we call that the absolute value. We multiply those and we get the coefficient that we have here, the radius length that we have here. And then if we add our two angles, 60 and 150, we get the 210 that we have here. And it literally is as simple as that. So even though the actual multiplying process can be a little brutal, we don't have to do it. We have this product theorem that says if I start with two complex numbers in trig form, so that's what this is saying here. I got a complex number in trig form, I have another complex number in trig form. There's just subscripts of 1 with the first to say that's the first one, and there's subscripts of 2 with the second to say, hey, that's the second one. So if we have any two complex numbers in trig form, then what happens when we multiply is out in front we end up with, let me use a highlighter here, out in front we end up with the product of the numbers out in front of our initial complex number. So the radius of the first one times the radius of the second one ends up being the radius of our product. And then we know our trig form is going to have our cosine plus I times our sine. So that component is going to be there. To get to the angle here, or the same angle here, we're going to add the corresponding angles from our original complex numbers. So if I add the first angle here with the first angle here, or vice versa, add the, not vice versa, but similarly, add the first angle here with the first angle here, then I end up with that sum. So I can see that I am adding those first two here, and I'm adding those same, it's the same angle, right? Either way, so it doesn't matter which pair we choose is what I was trying to say. Okay, So all we need to do basically is two things when we're trying to find the product of our two complex numbers. That's multiply what we call the absolute values or the radius lengths, and then add what are called the arguments, but those end up being the angles. So two key operations. Multiply the radius lengths and add the arguments, which are the angles. Multiply and add. Okay? Now in condensed form, I think it looks a little cleaner, so let me write it in condensed form, if in the condensed or the compact form. Okay, so in compact form, what we're saying here is if I have r cis theta, not q, r cis theta, and let's just call this r1 and cis theta 1 because that's going to be the first of our two complex numbers, and I'm going to multiply that by the second, r2 cis theta 2, that product is going to be equal to r1, r2 out in front, and then cis theta 1 plus theta 2. So again, we're going to multiply to get the radius here, and we're going to add these two angles to get the angle here. Multiply and add those two things. Okay? So while this is where all that comes from, we don't need to do that work every time. So let's try this in the compact form. Now I like the compact form better, so I might rewrite these both in compact form. If I want to find this product, this is really just 3 cis 45, and then I'm going to try to multiply that by 2 cis 135. And so again, multiplying the 3 and the 2, multiplying the radius lengths there gives me 6. And then there's going to be cis, let's add the two angles, the 45 and the 135. And 45 and 135 makes 180 degrees. And there it is. So 6 cis 180. Or if we wanted the expanded form because it started with a problem that had the polar forms expanded out there, we could say that the product would be 6 and then cosine of 180 plus I sine of 180. Boom, done. Piece of cake. Okay? So much easier than the work we had to do earlier, but hopefully have an appreciation of where it was coming from. Now the next one we're going to do the same thing. We're going to find the product, but this time it asks us to write the product in rectangular form, which means we'll take an extra step. After we have our polar form, we're going to convert it to rectangular form, which means we'll need it in terms of the x and the y components. So again, I like to, this one has multiply dot, this one has brackets, still means multiply, right? I like the condensed form, but we don't have to do the condensed form. If we want to just multiply here, we're going to get new radius length of 20, and then add the angles. So we can either choose to add this 120 with this 30, or we could choose to add this 120 with this 30, but it doesn't matter. The 120 plus the 30 means we're going to be looking at 20 times the cosine of 150 altogether, plus I times the sine of 150 again. Okay, so if you like to condense it and then multiply and add, you can. If you don't need to do that, you can see it from this form. It's totally fine. So here's our polar form of the product. Since it asks for rectangular form, we need to go another step. Again, we need to get this in terms of x and y. Now, we have formulas. Maybe don't write this if you're actually taking notes. We have a formula that says x is going to be equal to r times the cosine of theta. But here's our r and here's our cosine of theta. So I don't actually need to use this formula and do work here when what I have and what I need is already here. And again, we have a formula that says y is going to be equal to r times the sine of theta. Here's my r, again, here's my sine of theta. I can just do that evaluation and multiplication right here. So I'm not going to use these formulas to do any separate work when everything I need is right here in the polar form. So I'm going to evaluate what I have inside of the parentheses here. So to make this rectangular form, I'm going to leave the 20 for a second. I'm going to find the cosine of 150. So if you have your unit circle handy, that's super helpful. But 150 degrees, that has a 30-degree reference angle. So 30 degrees, I know I'm looking at my left hand right now, you could just envision this. 30 degrees hits the unit circle at radical 3 over 2 and 1 over 2. But at 150, or in quadrant 2, this is going to be negative. So those are the coordinates for our 150 degree angle. Let me get rid of all this crap. Okay, so cosine of 150 is going to be negative radical 3 over 2. Plus over here I have I times the sine of 150. Well, the sine of 150, that's going to be a half. So that's going to be I times a half, which is now a little strange. Let me just call this 1/2 I. And then to complete the rectangular form, I just need to distribute. So multiply here by 20 and multiply here by 20. And we end up with no more parentheses. We end up with our rectangular form. So 20 divided by 2 is going to make that a negative 10 in front of our radical 3. And then half of 20 again is going to make 10, but this is positive in front of I. And that's the rectangular form for this complex product. So this is the product in polar form. This is the product in rectangular form. Okay, not too terrible. Alright, so that's multiplying. Since we have that product theorem, the multiplying again becomes pretty basic. What we're going to look at next is the division, and I'm going to spare you the same thing basically happens, but instead of ending up with cosines of sums, we end up with cosines of differences. Now, I don't know if you remember anything about exponents, but the same operations that are connected with exponent rules, they're connected here. Let me back up just for a second. For example, actually I can do this here. Don't write this down if you're taking notes. When we are multiplying exponents, like if I was multiplying a 2x squared, let's say by a 3x to the 5th, we know this is a multiply problem, but the multiply happens with those coefficients, so we multiply the coefficients to get 6, and then we add these exponents to make x to the 7th, so it's multiplication and addition. That's what we saw with the product theorem for multiplying the complex numbers, the same two operations connected, multiplying the radius lengths and then adding the angles. So if I was thinking about exponent rules and division, so a quotient theorem, which we're going to look at next, if I was dividing, let's say 12x to the 9th by 3x to the 5th, then it's a division problem, so I'm dividing, but that division happens again with those coefficients, so I'd get a coefficient of 4. What happens to the exponents here is we would subtract and we would get x to the 4th. So it's the same thing for the quotient of our complex numbers. I'm going to end up dividing. In this case, it will be radius lengths, and then I will end up subtracting the angles. Okay, so that's what this quotient theorem says. If I have two complex numbers, so here's my first complex number divided by here's my second complex number, that we can divide the radius lengths, and then it's going to be subtracting the angles. So I can take these two angles and subtract them, or I can take these two angles and subtract them. It's going to be the same difference. It's funny to say that, in each of those, and that's going to be what represents our quotient. That's the quotient of those two complex numbers. So again, the key here is to divide the absolute values, which is the radius lengths, and then subtract the arguments, which are the angles. So divide and subtract. And again, I like the condensed form, so let me put that here for you too. If you had r1 cis theta 1 and you were dividing by r2 cis theta 2, we would say that quotient is going to be a quotient of the radius lengths multiplied by cis and then theta 1 minus theta 2. So just make sure that's the angle from the top minus the angle from the bottom. So the one that gets subtracted is the one that's in the denominator. Okay? So if you like the condensed form, separated form, whatever, just make sure you're connecting addition with multiplication, or multiplication with addition and division with subtraction. So for example, we're going to find the quotient here. And this one's expanded form. Maybe we leave it in expanded form. Maybe we condense it. It's really up to you. And I'll show this to you both ways. So let's say I condense the top. The top technically I could say is 27, and then our cis 45. And then on the bottom we have 9 cis and then negative 180. So again, it's division. We're going to be dividing the radius lengths here, and then it's subtraction. So we're going to subtract those angles there. So the quotient, 27 divided by 9 makes 3, and then we have cis, the difference, 45 minus a negative 80, minus a negative becomes a positive, and so we end up with 3 cis, 225. 225 degrees. And if you wanted to leave it in that condensed form, that would be totally fine. Or if you wanted to expand that out, that would be 3 times the cosine of 225 plus I sine of 225. So either one of those would be perfectly acceptable for the answer, again, condensed or not. But division and subtraction. Okay, so that's the quotient still in the polar form. If we look at the next example, we're doing the same thing, but after we get that polar form again, we're going to write it in rectangular form. So this one's already condensed, which is good, makes my work easy. I'm going to divide here, so 10 divided by 5 is going to give me a new radius of 2, and then it's going to be cis, the difference, subtract these two angles here. So I have negative 60 and I want to subtract out the negative 150. So that means I'm looking at 2 cis, and that's going to be negative 210. Can't write 200. Oh my gosh, turn my eraser on. 200 let's try that again. 210 degrees. And so if I asked you for the quotient, you could stop there because that does in fact represent the quotient, but it's in polar form. Since this one says to give the rectangular form, then I'm going to want to expand this out so I can evaluate. So this is 2 times cosine of negative 210 plus I sine of negative 210. And again, I could use formulas if I want, but everything I need to evaluate this is right here. So here's r times my cosine of theta, and here's r times my sine of theta. So let me just leave it as is and do the evaluating. Evaluating. I don't know why I said that so funny. Okay, so cosine of negative 210. Let me figure out where that's at. Negative 210. If I add 360 to that, I'm really looking at 150. Oh, that's the same angle I had earlier. So 150 degrees again. Negative 210 and positive 150 are the same place. So I know my coordinates, because I just did those, are going to be radical 3 over 2 and 1/2. But since that's quadrant 2, the cosine is going to be negative. So this is going to be 2 times the cosine of negative 210 becomes a negative radical 3 over 2. Plus I have I times the sine of negative 210 is going to be a positive 1/2. And I did it again. So I'm going to put that positive 1/2 in front of I. And then one last step, I just need to distribute that 2, multiply that cosine and that sine by r. And so my rectangular form is going to be negative radical 3 plus 2 times 1/2 is going to be 1i. And so that is my complex number in rectangular form. Okay? And I don't know why I boxed that one in. I didn't box anything else in. I feel like I gotta go back and do this now because I have mild OCD issues. I'm not going to the front, but there it is, okay? So hopefully the product and quotient theorems make this a reasonable process. And I just want to point out, by the way, that the angles that I put into our examples here, these happen to be nice angles that occur on the unit circle. If they didn't, then we would have to use a calculator to approximate. But if we can find exact values using the unit circle, then that's always going to be the goal. Okay? So I think you have enough to get going on your assignment, but as always, if you need some extra help, then just reach out, let me know. Until next time, take care.